Hi everybody. So this is your Chapter 3 Circular Motion PowerPoint, as well as a little video on some of the questions that we did for circular motion. Hopefully this helps. Just a few things of note that we need to remember for circular motion is that motion that involves any kind of circular pattern that we're looking at, whether it's roller coasters, whether it's skaters in a circle, or even cars on a road, all involve some kind of circular motion pattern. So we've already gone over some of these things about uniform circular motion. The one thing that I just want to remind you is that for uniform circular motion, we are saying that our speed of the object as it goes around in a circle is constant. So the speed is constant, the radius is constant. Two of those things that are constant. And we said, as this object moves in a circle, because the direction is changing, as the direction changes, it causes an acceleration because your direction is changing. So this is what causes your acceleration to take place. And we're looking at the tangent of the line, and that's what you're calculating when we are calculating acceleration for circular motion. Okay, this circular motion causes an acceleration. This acceleration is known as centripetal acceleration, which is center seeking. Your acceleration is pointing towards the center. When we do the calculations for circular motion, you find that your change in velocity that you see here is always pointing towards the center of the circle, no matter what those changes are. So VF minus VI divided by T, that will always point towards the center. Okay, so that is something that we need to remember. Now, of course, if there is an acceleration that takes place, that means there has to be also a net force that takes place. So these are some of the formulas that we've taken a look at. Acceleration equals to v squared divided by r, also 4 pi squared r over t squared, and also 4 pi squared r times f squared. So these are if you have your period. Okay, and this is if you have frequency. Okay, all right. Now you could do some of these questions on your own and check them out. Okay, just when we're analyzing forces, the one thing that we need to remember is that because there is an acceleration that is pointed towards the center of the circle, so therefore that acceleration is caused by a net force, and this net force is known as centripetal force. Now remember, centripetal force is the net force. It's just a name that is given to any object that is moving in a circular pattern, in a circular motion. So this Fc is your F net. This F net is always pointing towards the center in any circular object. Okay? All right, and it is not a force in nature. As I said, it is not a force in nature, just not like we've talked about net forces. It is a combination of forces. It could be caused by friction, it could be caused by tension, it could be caused by the normal force, or any other combination of two forces that could be taking place in that circular motion. The formulas, because AC is this, and we know F net equals to mass times acceleration, mass AC. So therefore we can join this into here, we can sub it in here. So we can have a formula which is F net equals to mv squared over r, or F net equals to 4 pi squared mr over t squared, or also F net which equals to 4 pi squared mr times f squared. It's the same thing. This is for frequency, that is for your period. Same thing. Okay, these are formulas that already exist on your formula sheet. So now what I want to do is I want to take a look at some sample problems, and hopefully we can help you with these sample problems. Okay, and so what I'm going to do is I'm going to get to my whiteboard, and for the whiteboard we're going to do a couple of questions. Now these are questions that we did in class, and these are just to help you. We did a couple of questions regarding centripetal forces. So first question that we did was dealing with when you have an object like a string that is being moved in a circular pattern, and we were asked to calculate. So there's a string, there's a ball at the end of the string, and we were asked to calculate the different forces that exists at the bottom and at the top of your motion. So this is a vertical circle. Okay, and the question is, what is the F tension here on the top, and what is the F tension at the bottom? Okay, now when we're looking at this, we can calculate and figure out what our FPD is. So when we're looking at it, now remember, for circular motion, inertia causes our objects to be pushed outward in all situations. And that force that pushes an object outward is not a real force. There is a name that is given to us. It's a fictitious force. And the name that is given to objects that are pushed outward is centrifugal force. Now this is not a real force. This is a force, as we know, is caused by inertia. The inertia is what's causing the object to be pushed outward. So in this object, in this question, the question where the object is moving in a circular pattern in a vertical circle, your centrifugal force is pushing outward, so your tension is going to oppose your centrifugal force. So there is your centrifugal force, so there is your tension inward, and of course you're going to have Fg. Here on the top, again, centrifugal force is pushing you outward, so your tension is downward, and your Fg is also downward. Both of those forces are downward, that are pushing you towards the center. This is what's causing your net force. So when we're calculating the net force at the top of the circle, so top of circle, we would do the following. We would do F net, which equals to, made up of the following forces, which is Fg plus Ft. Of course, F net being mv squared over r. So you would do mv squared over r minus Fg, which gives you Ft. This is at the top of the circle. Okay? Alright, at the bottom of the circle, your F net, again, has two forces, but this time you have two forces that are going in the opposite direction. Here they were going in the same direction. Here they are going in the opposite direction. They're going in the opposite direction. So you've got F tension inward, Fg outward, and the question is, which of these two forces is larger? Well, if Fg is larger, that object should be moving downward. So we know that Ft is larger than Fg, so we're going to do it Ft minus Fg, which equals to mv squared over r. So you're going to write it down as mv squared over r plus Fg, which equals to Ft. Now you could have situations where the question asks you, what is the minimum velocity that could allow for this object to move in a circle? So when we're thinking of a minimum velocity, that is meaning a velocity which just barely allows this object to move in a circle. In that situation, the assumption for minimum velocity or minimum frequency, and the assumption is that the tension at the top equals to 0 at top. Now that's not necessarily true for the bottom. At the bottom, your tension will always be larger than at the top. But if the question asks you that this is the minimum velocity required, then this is the assumption you're going to make, that the Ft at the top is going to be 0, so therefore your F net is going to be made up of only your Fg. Hopefully that is something that you understand. Please do ask these questions in class if you have any problems. Now I'm going to continue to another type of question that people have problems with, and this deals with cars on a ramp. So we're going to take a look at two, or depending on the time, we're going to take a look at two different situations where the car is on a ramp, and one situation is where the car is on a ramp with friction, and one situation is where the car is on a ramp without friction. Okay, let's just get the question for you. And this is from the old textbook. Okay, so if you've got the old textbook, if you've got the Nelson Physics with you, then you should be looking at the following. And this question is on page 130 of the old Nelson 12 textbook. Okay, sample problem number 2. And this question takes a look at a car of mass 1.1 times 10 to the 3 kg traveling on a frictionless curve, and this is what your object looks like. So this is your car, and this is you looking at the car from the back. So there is your road. This is 85 meters. Okay, the mass of the car is 1.1 times 10 to the 3 kg, and it's got a radius of 85 meters, and also it has got an angle of 19 degrees. So this is your theta right here. Now when we're looking at this, when we're solving for this, there are a few things that are different than other questions that we've done at an angle. So in this situation, your car is still at an angle, so you've got an Fn that goes this way, of course an Fg that goes this way, and instead of it going downward, now you have an Fnx and Fny that are going on the top of your hill rather than the bottom of the hill. Okay, because your Fnet is going towards the center, so it has to be parallel to the ground and not parallel to the hill. So when we are solving the question, we're going to take a look at the following. We're going to say in the y direction, Fnet y equals to 0. What are the forces that are in the y direction? Well, we've got Fny, which equals to Fg. So this is Fn cos of 19, which equals to mg. So therefore your Fn equals to mg divided by cos of 19. Okay, now when we are solving for the x direction, we're going to say Fnet x, of course, is not 0. It's ma or mv squared over r. Okay, in the x direction, what are the forces? We have Fnx. Now remember what I said was the curve is frictionless. So your Fnx is the only force that you have, which equals to mv squared over r. What is Fnx made of? Fn sine 19, which equals to mv squared over r. Now what we're going to do is we are going to sub this into here, and you end up with mg sine 19 divided by cos 19, which equals to mv squared over r. Now we know sine over cos is tan, so this becomes mg tan 19, which equals to mv squared over r. If we're solving for velocity, which is what we are, we're going to bring this up, so this becomes mgr tan 19 divided by m, which equals to v squared. The m and the m cancel out, and you are left with v equals to the square root of gr tan of 19. Now as I told you before, the expectation is that you are able to prove this on a test rather than just go straight to this formula. Okay. Now what happens if this is not the case? What if we have a car that is at an angle? What if the car is at an angle? Then what do you do in that situation? And if there is friction for that car, then what do you do? And in that situation, we're going to set up the equation slightly differently, and we're going to do the following. And hopefully I do have time for this. So what you're going to have is you're going to have your car still at an angle like this, and we're going to have two situations. So your Fn going upward with Fnx and Fny and Fg. But now you're also going to have static friction, which is going to go this way, and the static friction Fs is also going to have two components. And this is going to be the breakdown of the car. So again, you're going to do exactly the same thing in terms of the y direction, which is 0, and the y direction is going to be made up of Fny, which equals to Fsy plus Fg. Okay, and the x direction is going to be Fn